In this video, we'll look at the fundamental theorem of calculus. So the fundamental theorem of calculus is just that, fundamental and amazing. It is the theorem that makes the formal connection between the two main pillars of calculus, derivatives and antiderivatives, or integrals. Okay? And we'll see that when we actually use it, it is quite amazing. So let me show you exactly what it is, and then we'll do some examples. So we call this thing the FTC for short, and really it says the following. It says that if f, so my function f is continuous, on some x interval a, b, okay, from a to b, and capital F is the antiderivative. It's the antiderivative of f. Then I have the following. The following expression. It's a connection between the integral or antiderivative part of calculus and the derivative part. That is, we have the following. Then we have that if you integrate from a to b, or you find the antiderivative from a to b of my function f of x dx, it's exactly equal to the antiderivative at these values, the difference of the two. In other words, it's f of b minus f of a. That's exactly the fundamental theorem of calculus. And again, what it says is, if I want to compute the definite integral of my function f, in other words, I want to know the area underneath the curve f between points a and b, it's exactly equal to the difference in the antiderivative at the values b and a. Okay, so it's capital F at b minus capital F at a. And this is amazing because it gives us a real connection between the integral part of calculus over here and the derivative part of calculus, which is over here. Okay? Keep in mind that, of course, by definition, f's derivative at x gives me my original function back, right? Because that's what it is. It's the antiderivative. So here's the fundamental theorem of calculus. Let's actually put it to work. All right, so here it is. Here's a simple example using the fundamental theorem of calculus. That is, I want to compute this definite integral. Again, with a definite integral, we want a number as an output, not a function, because it's definite. So to compute the definite integral, all I need to do is to determine the antiderivative and then plug in the endpoints. That's what the fundamental theorem of calculus says. That's amazing. That means I don't care about any other point along the line, just the endpoints. This is why we spent so much time talking about antiderivatives, so we can compute things like this. This one's easy because we know the antiderivative of polynomials. So let's go ahead and compute. And we can do this in the same way we did before, which is all we need to do is take this constant out front and deal with this as an antiderivative. Even if we have sums or differences, we can do the same thing. We can break it up into small pieces, just like before, no different. The only difference is that in the end, we have to plug in values to get an actual number out. So let's compute. Here we've got a 5. We've got this integral or antiderivative sign here, -1 out to 3, t squared dt. But we know the antiderivative of that, right? We just add 1 to the power and divide by what we found. So this is really 5. It's going to be 1/3 t cubed inside. And then what I draw is a symbol that just means that I need to plug in the endpoints. So this symbol just means I need to evaluate at 2 points. And on the bottom, I'll put -1. On the top, I'll put 3. So the bar just means I'm evaluating here and here. And so what I have here is, since this is the antiderivative, right, I've certainly computed that capital F of x, the antiderivative of this, is 5/3 t cubed. Right? That's the antiderivative, or at least the antiderivative that matters in this problem. Okay? So for this, because we're talking about a definite integral, we determine whatever constants would be there. So this is the antiderivative that we care about here. And what I have is, I just need to evaluate this value at these 2 points. Right? So I'm going to put b in first. B is 3. Right? This is b. this is A. So I have 5/3. I got to put B in, so that's 3 cubed minus plug in A for T. So I have 5/3 A. A is -1 cubed. Okay, and all I have to do is compute these values, and I'm going to get a number out. That's what I want. So let's continue and finish. What we have here is, well, this is 3 cubed. One of those 3's is going to cancel, and I'm going to get a 9. So 9 times 5 is 45. Minus, well, -1 cubed is going to be -1. So actually, the -1 is going to make this a positive. So we're really just going to get a positive here, and you're going to have a 5/3. So if we want an exact value, let's put it into one complete fraction. And we just turn the 45 into thirds, and 45 into thirds becomes 135/3. And so putting that together, you're going to have 140/3. So when all the smoke clears, my answer is 140/3. So this is the exact value of the area below this particular curve from -1 out to 3. Okay? And so we know the picture of what this kind of looks like. It's really some kind of quadratic function. And all I'm saying is that if we start at -1 and go out to 3, the overall area beneath that curve, above the horizontal axis, will be this value, 140/3. Let's look at another problem. This time, our function is slightly more complicated. Again, I want to compute the definite integral of this function. So I write down this expression. Really, all I need to do is to determine the antiderivative. However, this function is more complicated. I can't just look at it and know what the antiderivative is. So in particular, let's use u substitution. I think that'll help us. Because again, what's giving us trouble is the stuff underneath the square root. 3 is just a constant, so I can throw that out front. So that shouldn't give us any trouble at all. In particular, if I let u be 4x plus 1, then of course du is 4 dx, which means that if I solve for dx, 1/4 du is really dx. So I want to turn this problem into u. The thing I have to be careful of is when I'm doing definite integration, when I'm making a substitution, I have to really keep in mind that I've changed variables. So I have to, likewise, change my endpoints of integration. Okay? So I have to be very careful here, and that's what will cause some difficulty. In particular, this is x, right? X is 2, and x is 0. But if I change and go to u, I have to make sure that I make the corresponding change in u. Okay? This is, of course, b, this is a. I start down here and go up here. I should write that b, and this is a. All right? So let's go ahead and use this substitution to make our life easier. So first of all, I'm going to pull the 3 out front, put an integral here. I'm going to leave the endpoints for now. I'm not going to put any values there. I'll deal with that in a minute. Let me first write down what I have for my integrand in terms of u's. So really this is going to be the square root of u, and dx is 1/4 du. Okay? But of course, with the 1/4, I can just throw it out front again. I don't want to deal with it inside of the integral symbol there. So I put it over here. It's outside there with the 3. Now the next thing I'm going to do is actually deal with the endpoints here. Again, I have to change them because now I have a function or a problem in terms of u. In the end, all I care about is that I have a number, so it doesn't matter whether I work with u's or work with x's in the end. Okay? As long as my numbers correspond properly, that is, that I take care of these endpoints. In other words, make the endpoints relate to u, not x. So again, I'm going to do that by looking over here. U is defined as being 4x plus 1. So that means that u is equal to, well, when x is 2, u is, plugging 2 in here, 2 times 4 is 8, plus 1 is 9. Okay, when x is 2. So when x is 2, u is 9. When x is 0, correspondingly, I look at my definition of u. So I take x equal to 0, in my definition of u, and I get 1. So when x is 0, u is definitely 1. So I change my endpoints of integration. That means this 0 becomes a 1, and this 2 becomes a 9. That's because I've changed to a variable of u. And now I don't even have to worry about x at all. I can just work with this problem and forget about the previous problem. Because again, all I want is a number in the end. I'm not looking for a function this time. So I just compute. Now I can actually compute the antiderivative of this. In fact, I can do it fairly easily because it's just a power rule. So this is going to be a 3/4 here. The antiderivative is, well, this is u to the 1/2 power, right? I'll write that. So this is really u to the 1/2 power. Again, I just go backward. I can find the antiderivative. I add 1 to the exponent, so 1/2 plus 1 is 3/2. And then I write down here the reciprocal of that exponent I found. So this is 2/3. And now I write this bar here because I have to evaluate at these endpoints, 1 and 9. So in the end, let's deal with this constant first. The constant becomes, well, look, I got a cancellation. 3's cancel. Moreover, 4 is 2 times 2, so one of those 2's cancel, and I just have a 2 down here. Okay? So in fact, I have a 1/2 u to the 3/2. This is my antiderivative. I'm going to plug in my 9. So this is now 9 to the 3/2 power. Minus, again, this is my antiderivative. The coefficient out front is 1/2. And I'm going to plug in my other endpoint, which is 1. So 1/2 of 1 to the 3/2 power. Okay? Again, I probably should more clearly write what the antiderivative is here. This antiderivative was really 1/2 u to the 3/2. And all I did is I used the fundamental theorem of calculus by plugging in the endpoints. First, I put in b, which was 9. And secondly, I subtracted that from entering in a, which is 1. Okay? All I have to do now is compute this number. And in the end, I'll have my solution. So let's go ahead and do that. So let me write it up here to give myself more room. If I take 9 to the 3/2 power, I actually get 27. So this is really 27 over 2 minus, this is going to be, well, 1 to the 3/2 power is still 1, 1/2. So I get 26 over 2 in the end, and that really is also known as 13. So my solution here is 13. That is, geometrically, it means it's the area underneath this curve between 0 and 2. Or the definite integral is 13.